finished example 2, didn't we? I think. Okay. Let's look at example 3. All right. This is still an average rate of change right here. So average rate of change on the interval from 1, 3 to or -1 to 3. All right. This is not asking us for instantaneous rate of change. It is asking us for the average rate of change. So if we think kind of like a rough, this is a quadratic that has been moved to the right 2 and up 1. So if we think about, like, I'm just sketching a graph so you guys get a picture. To the right 2 and up 1. We're talking about like a quadratic that looks something like this. So that's kind of like a V shape. That should be more U-E. We're looking at something like this. So if we're thinking about where this cross, oh gosh, I probably should have drew that a little taller. Hold on. Let's drag this down. So made it too steep. Let's make it look like that a little bit more. All right, rough graph here, very rough graph. So f of -1 is going to be like over here somewhere, and then f of 3 is going to be over here somewhere. Just rough sketch. I'm just doing this so you can picture what's happening. What we're looking for when we're looking for average rate of change is the slope of that secant line, that line that crosses through those 2 points. Okay? So this is something we can find without knowing any calculus. It's just, I mean, everything you need to know to do this you learned in Math 1. Obviously you didn't learn this in Math 1, but you learned the things that you need to know. So f of -1 would be -1 minus 2 squared plus 1. So -3 squared plus 1, which is 9 plus 1, which is 10. So that first point is -1, 10. Then we need to also find f of 3. So f of 3 would be 3 minus 2 squared plus 1. So that is 1 squared plus 1, which is just 2. So that's the point 3, 2. So average rate of change on -1, 3 for f of x would be, we're just doing slope formula, 2 minus 10 over 3 minus -1, which is going to give you -8 over 4, which will give you -2. So when you see average rate of change of a function, you should be thinking slope between the endpoints. Okay? Average rate of change, it does not matter the speed at any particular point, it's the overall. If you drive from here to Winston and it's 50 miles away and it takes you 1 hour to drive it, your average rate of change was 50 miles per hour, right? It doesn't matter what happened in the middle, how fast you were going in the middle. Average rate of change is just the from end point to end point and the amount of time that it took you to do that. Okay? All right, questions?
Why can't we do that kind of math? Can I color the guy for him?
Yeah, not right now. But if you want to take it, color it later.
Kind of guy.
Yeah, he did miss one. I don't know what he was.
How did he miss one?
I don't know.
No, he didn't. Oh, yeah, he rewrote it 7 times.
Yeah.
You got 8 the first time, and then you got 2.
Yeah, 7 plus, you said 7 plus 3 was 8.
Yeah. Yeah. All right. Okay. Let's talk about instantaneous rate of change at a point. I have made us a Desmos example. It's pretty impressive. Check that out. Look at all that right there. It's nice. All right. You don't necessarily have to know how to do that. All right. So here's the idea that we are looking at. All right. So I have a function. I made this so we can change the function. We'll put it back to something in a minute. I'll show you how it looks on different things. Okay. So I have a point right here, x f of x. All right. And A is the point where I want to know my rate of change. Okay, so we're thinking about now instantaneous rate of change. Not average rate of change, not how long it took you to get to Winston and your average speed. We want to know like radar gun speed, right? How fast you're going at a single point. So if I'm looking at this, right here I have what we call a secant line, right? And it would give me the average rate of change between these 2 points right here. All right, so if I found the slope of that line, it'd give me average rate of change. What I am looking for is I'm looking to be able to approach that point, okay? As my x gets closer and closer and closer to that point, my line will get closer and closer and closer to being a perfect tangent line there. So this would be the same even if I change the function. It should still work. So if I want to do something like just a quadratic x, oh wait, first let me get, oh wow, that's kind of cool looking. If I do x minus 3 to the second plus 2, right? Where'd my x go? Oh gracious, lost it. There it is. So if I take that x, if I go, let me make it closer no more. If I take this x right here, as my x gets closer and closer and closer and closer to that point, my line gets closer and closer and closer to being a perfect tangent line, right? It disappears whenever I get there because of the way that it's calculated over here. But if I get closer and closer, and I could approach from either side, right? As I approach that point, my line gets closer and closer and closer to being a perfect tangent line. Okay? So, let me split screen this. So let's think about what is happening here. Oh, shoot. What's happening? There we go. Okay. So, on this graph, oh wait, I don't really want to move A. I'll leave A right there. Alright. I want to find the instantaneous rate of change at A. So, I'm going to be dealing with my slope formula between those 2 points. Right? I've got the point x f of x and a f of a. So I could do, oh wait, first I gotta, I don't really want that. Click over here. Alright, I could do f of x minus f of a all over x minus a. That is the slope of that black line right there for whatever x and a are. F of x and f of a are my y coordinates. X and a are my x coordinates. So y is going top, x is going bottom. I could write this the other way. I could do f of a minus f of x over a minus x. You can do that if you want. It's more standard for books to put it this way, so I'm going to write it this way. Now, what's happening to know that instantaneous rate of change at A is that X is approaching A. It's getting closer and closer and closer to A. So to show that we want X to get closer to A, what can we do? We're going to do limit as x approaches a. Okay? This is your limit definition of a derivative at a point. You want to make sure you have that in your notes. You need to have this memorized. As much as I'd love to give you guys a note card on stuff like that, AP exam does not let us do that. So there are a couple things that we will get to that I'm just going to break down and let you use a note card on because they have barely put them on the AP exam at all. And I know you're going to forget them before we get there, but this is not one of them. You need to have it memorized. Most of these are not going to be calculator active problems.
Because you can write notes in the calculator.
You can, but AP is very, very smart about what they put on the calculator active section versus the inactive section. So any question where you would need to know this would be on the calculator inactive section. So you can put notes in your calculator. I don't usually have students do it at all because they are very smart about when it would be helpful and when it would not. And pretty much anything where it'd be helpful to have a formula is going to be on the calculator inactive section. And you do calculator inactive. Is that true? I think you do multiple choice calculator inactive first. So it would not be necessarily beneficial for it. So this we need to know. We can use this to find instantaneous rate of change at any point. I don't know why I used a t here instead of x, because my equation has an x in it. So make those match right there. So if this is how we use this. Our limit definition of a derivative was at a point is limit as x approaches a of f of x minus f of a over x minus a. So in this case, 3 is my a. Okay? Because 3 is the point that we're approaching. So this is what it looks like. Okay? You're going to do the limit as x approaches 3. So 3 is the a. Of f of x, I'm gonna write it out like this the first time. You don't necessarily have to write this step, but I'm gonna write it out like this. Minus f of 3 all over x minus 3. So f of x is just square root of x plus 1. F of 3 is what you get when you plug 3 into your equation. So that is the square root of 3 plus 1, which is the square root of 4, which is 2. You can write it over to the side if you want. You don't have to. You can just plug it in as a 2 right there. And then you got x minus 3. Now, if we plug in 3, what are we going to get? 0 over 0. And 0 over 0 is called what? Indeterminate form. It means we got to do something else. So we need to solve this limit. How would we solve this limit? What would we do to figure that out? Multiply by the conjugate. So we are multiplying by square root of x plus 1 plus 2 on top and bottom. And so when we do that, this will give us x plus 1. Okay? The outside and insides will cancel. We'll just have to multiply here and we'll get a minus 4. We'll have x minus 3 and square root of x plus 1 plus 2 there on the bottom. And then this is going to be x minus 3 over x minus 3 times square root of x plus 1 plus 2. The x minus 3's can now cancel. Okay, notice I have kept my limit notation this whole time, but I'm getting ready to plug in a 3 for the x. Once I plug in the 3 for the x, I can drop limit notation. So I'm going to just have 1 over square root of 3 plus 1 plus 2, which is going to be 1/4 whenever I calculate that. So, just to give you an idea of what this looks like graphically, let's change this to square root of x plus 1 over here, and let's put a at 3 right there. So what's happening is my x is approaching a. It's getting closer and closer to that point. I'm not going to get exactly to that point because it goes away if I do that. This line has a slope of 1/4. So up 1 over 1, 2, 3, 4. So that rate of change at that point exactly would be 1/4. Okay. And this is not an estimate. The graph is an estimate, but this is 100%. Definitely is 1/4. Okay. Questions on that? All right. Okay. Here is a little bit more of a word problem. It is still a very physicsy, dry word problem that is not like real life. But if you ever take physics, it's going to have a lot of positions and particles colliding in space and things like that. So the position of a particle moving along the x-axis is given by the equation here. What is the velocity? I've done this on, really honestly, they would probably use t's in this problem instead of using x's. Let's make it t's. I've been... They would probably use t's because you're looking at the position of the particle at a time. So I think you'd be more likely to see it with t's. It could be with x's, but probably t's. Okay? And so what is the velocity of the particle at t equals 1? So for this, we're using that limit definition. Limit as x approaches a of f of x minus f of a all over x minus a. Lucian, what is my a for this one? Not for this one. It's going to be 1, right? So it's not the number plugged in, but just the number that you're approaching. So if were you doing f of a, were you plugging it in? Yeah. So f of 1 is going to be 4 because you'll have 1 plus 1 squared equals 4. So we do need that. We're going to hold on to that. So we are doing here the limit as x approaches 1 of f of x minus f of 1 all over, you're right, t's. Gosh. I don't love t's either, but they do look like a plus sign. I would highly encourage you to make it look kind of curly like that.
I would much rather use an S.
Yeah. Oh gosh, you would rather use an S? No, definitely not. S is the worst variable there.
Kidding.
S is the only thing worse than an S.
Is
An O. An O would be worse than an S.
I don't know. I think an L sounds pretty good. A lowercase L.
Lowercase L's are bad. Yeah, if they ever use those, I always make them cursive, so I know they're not just a 1. But yeah. Yeah, I would make your T have this little, fancy piece here. It needs to be a fancy T.
Upside down lowercase D.
It's just an upside down F, the T.
Yeah. Yeah. It is just upside down F, isn't it? Just about. Pretty much. So, So f of t, for this case, is going to be t plus 1 squared. F of 1, we found over here, Lucian was kind of jumping ahead on that. We had 4. And the bottom is just, oh, I still didn't fix that one. That's a t. T minus 1. If I plug in 1, what do I get?
4 minus 4, and 1 minus 4.
4 minus 4 on top, 1 minus 1 on bottom, 0 over 0, right? So something's got to be done to this. What do you guys think we should try?
And you could expand it and then contract it.
Correct. Yes, we will expand and then contract. So we can just square double square here, t squared plus 2t plus 1 minus 4 over t minus 1. So then we will have the limit as t approaches 1 of t squared plus 2t minus 3 over t minus 1. What now? Because if I plug in, I'm still getting 0 over 0. We can factor, hopefully. Unless I've messed this one up. T plus 3, t minus 1. And you kind of knew it needed to be a t minus 1 there because you needed it to cancel or nothing else was going to work. And so now I'm going to plug in my 1. Because I'm plugging in, I can drop limit notation. 1 plus 3 is going to give us 4. Questions? Okay there. Okay, so here's some notation we have not seen yet. Okay, F with this little tick mark behind it, parentheses, -1. Okay, so let's make ourselves a note on notation right here first before we try the problem. Is not. F star was a specific thing just for that one problem that you won't see again. Like they defined it for that purpose. So F star you will not see again. This is a F prime. And I'm just going to put an X right there. It is read as F prime of X. It means the derivative of F at X. And that's, I mean, the title of this, actually no, the title of tomorrow's notes has derivative in it, but I haven't really used that word derivative yet. But a derivative is just the instantaneous rate of change of F at whatever number is there. So you're talking about the instantaneous rate of change. Remember, rate of change, you can also just think of that as slope. Right, so you're looking at the slope of that graph at a single point. So when you see F prime of -1, this means the instantaneous rate of change at X equals -1. Okay, so if we do this problem, we have to, right now the only way we know to do this is limit definition of a derivative at a point. We're going to learn something new tomorrow. So limit as X approaches A of F of X minus F of A all over x minus a, that same formula, right? That, if we wanted to, we could say f prime of a equals that, right? The derivative at a is going to equal this value right here. So we're doing limit as x approaches -1 of f of x minus f of -1 all over x minus -1. And so if we plug in our function, limit as x approaches -1 of f of x is 1 over x. F of -1, what do we get if we plug in -1 to our function? It's going to be -1 because we'll have f of -1 will be 1 over -1, which just equals -1. So we got right here, that's a -1 over, this is an x plus 1. Is that all right with you guys if I go ahead and just change that to a plus right there since we got a minus and negative? Okay, here. If I plug in -1 to this, I will get -1 plus 1 on top. I'll get -1 plus 1 on bottom. I'm getting 0 over 0. So I need to do something here so that I don't get 0 over 0. What could I do?
Is there a way to like cancel?
Yes, there is. But we can't just like mark them out. They don't just mark out. We can multiply by something that'll cause things to cancel. So
Would it be like that?
we want to get rid of that denominator right there because that denominator is causing us to have a fraction inside of a fraction, right? So if there is only one single denominator, my favorite way to do this problem is to multiply the top by x, which I can do if I also multiply the bottom by x. And the reason that that works so nicely is because when I do x times 1 over x, what do I get? I just get 1 because this x right here is like x over 1. Those x's cancel, or if you want to think of it this way, you're going to have x over x, which just does equal 1, right? So right here when I distribute that, I'm just going to get 1. So I got limit as x approaches -1 of 1 plus x times 1 is just going to be x over, don't multiply the bottom together because you want things to cancel, so you're just going to have to factor it right back out if you do. Will anything cancel?
You could take out like a
Were you going to say a negative? Do you need to take out a negative on this one? No, because it's a plus. If that was x minus 1, you'd be exactly right. Does it matter if it's 1 plus x or x plus 1? Those are the same. Even though they look a little different, they're the same. So then I can plug in 1 over -1, and I get -1 as my answer. Okay. This half of the room, I want you guys to do B. This half of the room, I want you guys to do C. Okay? So try those for me. parentheses, the same thing that you got. Right side of the ring. A little bit trickier. I might show you here so you guys can see. You're okay. You did it. You did it. Okay, so you're not.
I just did the same thing that we did on the first one, except for
Yeah, where is that? That would be because it was
there, but it just was because that was
All right, I'm gonna just put up mine for the first one. So you should get -1 also for B. For this one, we had to do exactly what you were kind of wanting to do the first time, Luke, right? Because if you multiply by x on top and bottom, when you distribute, you will get 1 minus x. That does not cancel with x minus 1 because they're not equivalent. So you would have to factor out a -1 to make it x minus 1, and then you can cancel. You'll plug in your 1. You still get -1 for this one. Okay. Questions on that? No, if you didn't have that one, you might not have time to write it down, but we'll move on. All right. The second one, I want to show you 2 different ways to do the problem. Okay. You could do this on A and B as well. But the issue with this one, Jeremy, here. The issue with this one is that whenever you plug this in, so I can see. Write this up. So we're down here at the bottom here, and so when you plug it in right here, you should end up with 1 over x plus 1 over 2 equal over x plus 2. So the issue here is that we don't have a single denominator like we had on the other ones. So what you can do is you can find a common denominator, like Jeremy did here, which would be 2x, and multiply the top and bottom by 2x. Here is why that works. Whenever you have turn giant on me. Whenever you have 2x times 1 over x plus 1/2, when you distribute, you're doing 2x times 1 over x. 2x is over 1. That x cancels with this x. You just get 2. So that's what you see Jeremy has right there. And then you distribute right here, 2x times 1 over 2. That's over 1. The 2's cancel, and you just get x. That's what Jeremy has here. So you can multiply by that common denominator, and then you get a 2 plus x. It cancels with the bottom. You plug in -2, and you get -1/4. Okay, questions there? Okay, Kendall did hers differently, I think. So let's look at hers. Because she's not done, but she's on the right track here. So let's look at what she's doing. She's just the only person I saw doing this, but I want you to know this is an option for this. So she plugs it in. It looks very similar to Jeremy's up here. We got the 1 over x plus 1/2. Rather than multiplying top and bottom by something here, she's getting common denominators. Okay? So she multiplied this by 2 right here on top and bottom. And she multiplied this by x on top and bottom so that she would have 2x as her common denominator. So it would look like this. Then she can write them together. She's got 2 plus x over 2x over x minus 2. And so, limit notation is gone, but it's okay. We'll forgive her for that. So this would be 2 plus x over 2x times, oh, I see what happened right here, Kendall. Here's where you were running into an issue. Right here you had a plus x. For some reason it changed to a minus x right here. So she was running into an issue, but the issue was just because she miscopied right there. So that right there should be a plus. Let's fix it and make it a plus. Right here. Right. Oh, let's use a color you can see. So that is a plus 2 right there. So now these can cancel right there. So these actually will cancel because that's a plus right there. And then you'll plug in 1 over 2 times negative 2. And you will also get negative 1/4 right there for that one. Okay, so I want you guys to see that as an option as well. Both of those are mathematically sound ways to do this problem. Honestly, it's really up to whatever makes more sense to you on what you prefer to do. I like whenever you just have a single denominator. I like just multiplying because it's quick, but sometimes that may be a little bit easier. So your assignment tonight is going to be not written right there. What page is it? It's on Canvas. It's 1 through 10, but I can't remember the page.